In this example, we are going to talk more about 3D rotations and 3D kinematics. The 12 meters ladder of this fire truck rotates in two directions simultaneously. By looking from the top view, we can see that the ladder rotates at rate of 0.15 rad per second, and accelerating at 0.8 rad per second squared. And by viewing from the side view, we can see that the ladder rotates in the other direction at constant rate of 0.6 rad per second. And constant here means that it does not accelerate during rotation in this direction. The first step to solve this problem is to start by setting up an appropriate 3D coordinates. And the problem we have here is to find the velocity and acceleration of the top point of the ladder. Let's give it the name A. And the problem we have here is to find the velocity and acceleration of the top point of the ladder. Let's give it the name A. And we will find these values at specific moment when the ladder makes a 30 degrees angle with some reference point. Based on the right angle triangle, and knowing that the ladder is 12 meters span, we can find the position vector r that goes from the central reference point to the top of the ladder. Notice that this vector has y and z components. Now we start the math part. And let's first build the angular velocity omega vector. Notice that the ladder rotates on x and z axis, but no rotation on y axis. Now we get the linear velocity equation for point A. And it will be referred to some zero velocity point. And this point will be the base of the ladder. Now we get the position vector r. And again, the reference point, which is the base of the ladder, will have a zero velocity as it does not move at all. Now applying these values in the equation, and doing the cross product, we can calculate the velocity of the point A. Now we go to the next part, working on the acceleration of the point A. Now we have the acceleration equation, which contains the reference point acceleration and both normal and tangential components. And again, the reference point has zero acceleration. Knowing that the angular acceleration alpha is the time derivative of the angular velocity omega. Notice that this derivative has 6 parts, as we need to consider the rate of change of not only omega components, but also the unit vectors themselves, because these unit vectors also change over time when the system rotates. Again, there is no action over the y-axis, so we can minimize the expression. Applying the values in the equation, remember that the ladder rotates at constant omega around x-axis, so the x-axis alpha will be 0. But we still have alpha value for the z-axis. Now we need to choose the big omega so we can calculate the unit vector derivatives with refer to it. Let's choose the big omega to be the one over the z-axis. Now we apply these equations and find the time derivative of the unit vectors. Notice that the k dot is 0, as the cross product k cross k is 0. And this is because the z omega was chosen as the reference of rotation. We finally apply the values and find the angular acceleration alpha. As you can see, alpha has two components: the z component and the y component. The z component exists because the latter accelerates when rotating around z-axis. And the y component exists because the unit vector of the x-axis changes its direction toward the y-axis. The last step is applying all values we just found in the acceleration equation. Doing all cross products and arithmetics, we find the acceleration of point A at the top of the ladder at the instant it makes 30 degrees with the reference base. In this example, we have learned how to find the linear velocity and acceleration of a specific point within a 3D rotating objects. We also learned that choosing the right coordinates and the right reference point are the keys to solve such a problem. Soon we upload some more real-world examples of 3D rotation problems and explain how to solve them in a step-by-step manner. Thank you for watching.